This video is on rational function graphing. We're going to focus on oblique asymptotes today. First, we're going to warm up by using long division to find the quotient. So x cubed plus 7x squared plus 14x plus 3. If I divide that by x plus 2, I have x squared. I get 5x squared plus 14x down here. Then I will have a plus 5x. So 5x squared plus 10x, change the signs. I get 4x plus 3, so I need plus 4. That becomes 4x plus 8, change the signs, negative 5. So the remainder is negative 5. So I would write this as x squared plus 5x plus 4 minus 5 over x plus 2. So that's what happens when you divide x cubed plus 7x squared plus 14x plus 3 by x plus 2. A rational function can actually cross over a horizontal and oblique asymptote. And one of the reasons why we talked about using long division is because that's going to be really important when we determine intersections of oblique asymptotes. So if and where a rational function intersects a horizontal asymptote, first we find the asymptote, then we set the function equal to the equation of the asymptote, and then we solve, and we determine that if there's any sort of value where it crosses. For an oblique asymptote, we use long division to find the equation of the asymptote, and then if there is a remainder, we set it equal to 0 and solve for x, and that will be the x value of the location where the rational function crosses the oblique asymptote. Let's do some practice. Graph each thing, find all the important information, necessary information. So here we go. Number 1, x plus 2 over x squared plus 1. X-intercepts are where the numerator equals 0 and the denominator doesn't. So that's negative 2, 0. Y-intercept is when x equals 0. 0, 2. Vertical asymptote is where the denominator equals 0 and the numerator doesn't. That never happens. Horizontal asymptote or oblique asymptote, since the bottom power is bigger than the top power, this is the line y equals 0. And the removable discontinuity would be if both the numerator and denominator are 0, there would be a hole. There are none of those in this problem. So I'll graph everything that I know. I know that we have the point 0, 2 and the point negative 2, 0. And I also know that we have an asymptote horizontally at y equals 0. In order to graph this, I have to use all of this information now. So I know that I'm going to be approaching the line y equals 0 as I go off to infinity. And I'm going to be coming from this point. I know that I'm going to cross here, and then I have to come back toward the line y equals 0 again. Now notice, this is the first time that we've intersected a horizontal asymptote. So our horizontal asymptote is at the line y equals 0, and I intersected it at x equals negative 2, and that's because if I set the function equal to the horizontal asymptote, notice that the numerator, being negative 2, would make this equal to 0. So that is this function. Do I know that this is the peak or the maximum? I don't, but I would be able to find that out in calculus if I wanted. Number 2, if I take a look at this function, x-intercepts are where the numerator equals 0 and the denominator doesn't. So I guess I should figure that out by using the quadratic formula. So x equals negative b, so that's 1 plus or minus the square root of b squared, which is 1, minus 4 times a times c, all over 2 times a. 1 minus 4 gives me negative 3 on the inside of the square root. So that means that this would be an imaginary solution, so I do not have any x-intercepts. Y-intercept would be what happens when I sub in 0. So I get 0, -1 when I sub in 0 for x. Vertical asymptote is denominator 0 and numerator not equal to 0, so that's x equals 1. This has an oblique asymptote because the power on the top is bigger than the power on the bottom. And so that means that I'm going to have to use long division in order to figure that out. So I'm going to use long division. X minus 1 is dividing x squared minus x plus 1. So x would be the first one that goes up here. X squared minus x. Oh, that works out really nice. So when I subtract these two things together by changing the signs, these things both go away, and I pull down a 1. So that means that this function is the same thing as x plus 1 over x minus 1. So my function that it looks like my asymptote is the line y equals x, and then I have a remainder. Removable discontinuity would be if the numerator and denominator are equal to 0. That never happens in this problem. So I now can figure everything out. So I have a vertical asymptote at x equals 1. I have the y-intercept at 0, -1. I have a horizontal asymptote, or I'm sorry, a slanted oblique asymptote. Y equals x. And now my job is to figure out what this graph looks like. So this graph will go down as I approach the vertical asymptote, and it will kind of look something like this. Then this is generally speaking what it looks like. The other thing we have to do is figure out, does this ever intersect my oblique asymptote? So the procedure for determining whether it intersects an oblique asymptote was to set the remainder equal to 0 and solve for x. So I'm going to set the remainder equal to 0, 1 over x minus 1. This will never equal 0 because it just can't. The numerator is equal to 1, and that means it never equals 0. Therefore, there is no place where this intersects the oblique asymptote, and that is what my graph looks like. Problem 3. X squared plus x minus 12 over x squared minus 4. First thing I'm going to do is factor this because it's factorable. So x plus 4, x minus 3 over x minus 2, x plus 2. So that gives me a lot of information. First of all, there are no holes, no removable discontinuities because nothing is the same on top and bottom. Vertical asymptotes are at x equals 2 and -2. Y-intercept is what happens when I sub in 0 for all of my x's. So I'm going to go back to the original non-factored thing. That makes it easier. -12 over -4 gives me y equals 3. My x-intercepts are when the numerator equals 0 and the denominator doesn't. So that's -4, 0, and 3, 0. My oblique asymptote or horizontal asymptote, well, since the powers are the same on the top and bottom, that means that I know that I have a horizontal asymptote, and it's what happens when I divide the coefficients out. So I have y equals 1. So there's a lot of stuff going on here. Big problem. So I have -4, 0, and 3, 0. I have 0, 3. I have vertical asymptotes at 2 and -2. I have a horizontal asymptote at 1. So I have all this information. The only other thing I need to figure out is, does my graph ever cross the asymptote? So I could use long division if I wanted, but I can also just set this equation equal to 0. And that may actually be easier in this case than using long division because I didn't have to use long division to get anything else. So what I can do is I can set the function equal to my horizontal asymptote, and then multiply this over. So I have x squared plus x minus 12 equals x squared minus 4. And then what I would end up doing is subtracting the x squareds, and I add the 12 over, I get x equals 8. Actually, in this problem, I can't really use the long division method anyway, because the power on the numerator and the power on the denominator are the same. So I'm just going to set this equal to my horizontal asymptote. I figure out that at x equals 8, I actually cross my horizontal asymptote. So I'm going to put a point at 6, 7, 8, comma 1. So this is kind of what my graph looks like. It never crosses the asymptote over here. It's going to go down forever. Then this has to go from the top, because the multiplicity is 1 of that. It's going to hit this point, then come back up because it never crosses the horizontal asymptote. And then it's going to start down, crosses, and then comes back at some point. So this is kind of what my graph looks like for number 3. Number 4, x-intercept is at 0. Y-intercept is at 0. Vertical asymptote would be at 1. And it has multiplicity 2. So that means that whatever direction it goes, it's going to go up from both sides or down from both sides. Horizontal or oblique asymptote, well, it's pretty clear that it will be something in the numerator is bigger than the denominator. We have no removable discontinuities. So what I need to do is I need to figure out what this looks like. So if I have 3x cubed divided by x minus 1 squared, that's x squared minus 2x plus 1. So I need a 3x over here. That becomes 3x cubed minus 6x squared plus 3x. And then this becomes positive 6x squared, because I have to change the signs, minus 3x. So then I have a plus 6x squared minus 12x plus 6. Then I have to change the signs again, so I would end up with 9x plus 6 as my remainder. Oh, I'm sorry, 9x minus 6. That would be bad if I got that wrong. So this is the same thing as saying 3x plus 6 plus 9x minus 6 over x minus 1 squared. So this is my function. So that means my horizontal asymptote is y equals 3x plus 6. So as I graph this, I have a slope of 3 and a y-intercept of 6 as my asymptote that it kind of looks like. I have a vertical asymptote at x equals 1. And then I have intercepts. I should graph that in a different color. At 0, 0. So the only thing left to figure out is whether this ever intersects our slant or oblique asymptote. So what I would do is I can set the remainder equal to 0. So I have 9x minus 6 over x minus 1 squared. Set that equal to 0. And what I'll realize is that just means the numerator has to be 0. So the numerator is 0 when x equals 6 over 9, which is 2/3. So when x equals 2/3, my function crosses the oblique asymptote. So what I'm going to do is I'm going to take 2/3 and substitute that into the original equation. And if I substitute it in in the interest of time, I'm just going to tell you that the y value is 8. So at 2/3, 8 crosses the oblique asymptote, and that would make sense because 3 times 2/3 is 2 plus 6, which is 8. So what happens is, as I approach my vertical asymptote, it's going to go up forever, and then I have to approach my slant asymptote as I go down forever. And then I have this behavior as I'm approaching the asymptote from the right. Remember that because I have multiplicity 2, as it goes up forever on the left side of the asymptote, it also has to go up forever on the right side of the asymptote. So my graph will look, I know it's a little bit harder to see because I have other things going on. So here's my asymptote. And here's the graph. I'll draw that again. Here's my asymptote, vertical asymptote, and this. I have this intersection. I have this intersection. And I know this goes up forever. So it's going to behave like this and like this. In the interest of time, I've already calculated problems 5 and 6. So I've done all the long division. I've looked at factoring in number 5, where I factored out the x cubed minus 1 using SOAP and everything. So looking at number 5, x-intercept is at 1, 0. This part, if I use the quadratic formula, I would get imaginary answers. Y-intercept is when you plug in 0 for x. Vertical asymptote is when bottom is 0. The horizontal, well, it's not a horizontal, the oblique asymptote is as shown. It's at x squared minus 2x plus 4. After you do the long division, then there's no hole. So if you look at this function, when I graph it, looks a whole lot like the parabola x squared minus 2x plus 4. Now, how do I make sure I get everything right? If I plot 1, 0, if I plot 0, negative 1/2, and I know I've zoomed out so that you can see it, but I plot 1, 0, and 0, negative 1/2, I put an asymptote at x equals negative 2, and I graph this parabola. Remember, you can find the vertex by doing negative b over 2a, which is 1, and then plugging that in. So you get the vertex of this to be 1, 3. So you can plot this parabola, and you graph it, and you kind of see how this goes off like this, and then this will go down to infinity because it does not cross the parabolic oblique asymptote. And then since this is x plus 2 to the first power, it's going to start on this side of the asymptote, come down, and then approach my parabola again. How do I know it doesn't cross the asymptote? Set the remainder equal to 0 and figure out that that never works. This problem, same deal. Numerator is 0 when x is 0. And then if I plug in 0 for x, I get 0. Vertical asymptote is at 1. So I would have a vertical asymptote here at 1. Y equals 2, or x squared plus 2x plus 3. That's what happens when I do the long division. And then I have a remainder of 4x minus 3. So this is what r of x looks like when it's divided out. So if I want to figure out if this crosses my oblique asymptote, I set 4x minus 3 over x minus 1 squared. Equal to 0. And I see that it occurs at x equals 3/4. So I've zoomed in on the graph a little bit. See how 3/4 as an x value is where it crosses the asymptote. Also, there's a vertical asymptote at 1. So because there's a vertical asymptote only at 1, I can kind of look at the graph as looking something like this. So I cross here, and I know that going up toward infinity, and I'm going to have, it's going to go in the same direction near my infinity because this is squared. So I know that it's going to go in the same direction. Now, how do I know that they're going up toward infinity? Well, what happens when I plug in numbers? Like, this is kind of confusing. Maybe it could go down. Well, first of all, I know that this is approaching my asymptote. So then I can graph this first if I was confused. And then since I had this squared, I know this is going to be going in the same direction. It's going to hit this, but it can't go down forever because it has to follow the asymptote as I go toward positive and negative infinity. And it's not supposed to cross the asymptote. It's just hard to draw on the smartboard. So it'll look something like this as I go up toward negative infinity for x. But how do I know that it never goes down? Well, if I look at these numbers, the numerator always has to be positive and the denominator always has to be positive or zero. So because that's the case, I can never have any numbers that are negative anyway.